Here we've got an energy problem where we have a disk and it's rolling up an inclined plane, and they give us sort of the mass, the radius, and the rotational speed and the linear speed at the bottom of the plane. How high does it get up the plane before it stops? This is going to be an energy problem. So let's first draw a picture as always. So here's our inclined plane, and at the bottom we have this disk, and it's rolling up the hill like that. And here we know that omega, the initial omega, is 5 radians per second, and the initial linear speed is 10 meters per second. So like the rotation, how fast it's rotating around, that's 5 radians per second, and the velocity, how fast it's going up the hill, that is 10 meters per second. How high does it get before the velocity is 0, and then presumably the rotational velocity is also 0? And we'll actually talk later about how these two have to happen at the same space given what we've been told in the problem. But for right now, let's just take it that it is. Okay, so we've got kinetic energy, both translational or linear kinetic energy and rotational kinetic energy, because it's got mass and it's going to have a moment of inertia, so that's enough to give us the the rotational kinetic energy, and it's got mass and it's got a speed, so that's going to be enough to give us the translational kinetic energy. So we can do this as a work is a change in energy type problem. All right, so let's first look at work. Do we have any non-conservative forces doing work on this? And it's going to turn out that we don't. And this is actually the important phrase right here. Because if we draw a force diagram on this as it's rolling up, what are the forces we're going to have? We're going to have the normal force. We're going to have gravity. It's moving, get a different color, it's moving in that direction, so that's the displacement direction. Probably have one more force, and in fact we have to have one more force for a reason I'll talk about later. We're gonna have friction, and it'll either go up or down the hill. So let's sort of talk about which way that'll be. So here I've got my little stand-in for the disk, and it's rolling. This is our inclined plane here, and we're told it's rolling without slipping. So that means it's rolling like this, not like this, where it's sliding. So as it's rolling up the hill, this little disk is just rolling along, and each bit of the disk is touching just one point of the plane, and those two aren't moving relative to each other. As the disk moves up, a new part of the disk goes down to a new part of the plane, but it's not sliding. So there isn't actually any displacement as far as the disk relative to the plane when you're looking at friction. So it actually doesn't matter which way the friction is going to be, because there's no displacement, and said work is force times displacement. There's no work done by the friction force, but let's just kind of see which way it would be. If it was rolling, probably, and it were going to slip, it would probably slip like that. So the friction must be pushing up like this. But in this case, it's static. It's rolling without slipping. And we know the normal force does no work, because it is perpendicular to the displacement, and work is the force and the dot product of the displacement. So if those two are perpendicular, this vector and that vector at 90 degrees to each other, their dot product is 0. So that doesn't do any work. This is conservative, so it doesn't do any work. And this also, the friction doesn't do any work, because the displacement is 0. Each little bit of the wheel is touching just one little bit of the plane, and then a new little bit of the wheel will come down and touch a new little bit of the plane, but there's no displacement of the wheel or of the disk relative to the plane. So we don't have anybody doing work. That's not a conservative force. So then we can look at the energies that are changing, which would be the kinetic and the gravitational potential energy. We don't hear of any, explosions or sounds or anything going on there, so we don't have to worry about those other types of energy. So we'll have the final kinetic energy for rotation and the final kinetic energy for translation, the two different kinds of kinetic energy we've got here, and then the initial rotation kinetic energy and the initial translation kinetic energy, plus the change in the potential energy. So this was all kinetic here, and then potential, the only potential we've got is gravity, so it's the final gravitational potential minus the initial. And let's see, what do we know here? Final rotation and final translation. We are going to where it stops, so it'll stop rotating and it will stop moving up the incline. All right, so that is the first term here. And then we get the initial rotation, so that'll be 1/2 the moment of inertia times the angular speed squared, and then the initial translation, that'll be 1/2 the mass times the initial speed, and I guess these are initial, so I'll put the little 0 to match what I've got going up here. Oh, I don't actually have anything going up here. Okay, there it is. All right, and then the final potential energy. Let's say that height is 0 there, so the gravitational potential energy is 0 there, and we'll just call this final height, which is the thing we want. We'll call it h, so the final potential energy will be mass times g times h, and the initial will be 0, because it starts at the bottom. And all of this is equal to 0 because no non-conservative forces are doing work. All right, and we can now, this is negative, a whole bunch of zeros. Actually, let's just go ahead and write this a little bit more neatly. So this is negative 1/2 moment of inertia times the initial rotational speed plus 1/2 mass times the initial translational speed plus mass times g times h. This is negative. I'll pop it over to the other side of the equation. There we go. That's the thing we want. We're given mass, we're given initial speed, we're given mass, we know g, we know omega naught. I guess we need to figure out what I is. And they just tell us a disk, but let's make the assumption that it's a uniform disk, because then I of a disk, a uniform disk, that's rotating about its center, which is basically what's happening here, rotating like that, that's going to be 1/2 m times the radius squared of the disk. We just solved that in our other problem. So this will be 1/2, plug in this for the moment of inertia, times omega naught squared plus 1/2 mass v naught squared plus mgh, and every single term's got a mass, so let's cancel it. There we go. All right, and then 1/2 times 1/2 is 1/4 r, oops, forgot the r squared there, r squared omega naught squared plus 1/2 b squared equals g over h. We'll divide both sides by g, and we will get h equals 1/4 r squared omega naught plus 1/2 v naught squared over g. And now we can plug in our numbers. R, that's 2 meters. Omega naught, that's 5 radians per second squared. V naught, that's 10 meters per second squared over g, 9.8 meters per second squared. Go ahead and get our calculator. All right, this first term is going to be 25 meters squared here, radians squared from that over seconds squared. And remember, radians are kind of those units that just disappear when they're next to a meter. So we can just not write those and we get meters squared over seconds squared. Plus this one will be 50 meters squared over seconds squared. And that whole thing over 9.8 meters per second squared. And 25 plus 50, that's 75. 75 over 9.8, that's going to be a bit over 7.5, and it is 7.7. And then we get meters squared over seconds squared over meters per second. And that's the same as multiplying by the inverse, so seconds squared over meters. We have meters squared over seconds squared. The seconds cancel, one of the meters cancel, and we get a height in meters, which is what we're expecting. Okay, so now talking about why do we know that the rotational and the translational speed have to both be 0 at the top? And it turns out the key here is also this without slipping. So the without slipping is the thing that told us that friction wasn't doing any work here. So we ended up not having any non-conservative forces, but also without slipping means that it's really the rotation that is causing the translation. So if I go like this, you can see that if I rotate faster, I'm going to move faster. And if I rotate more slowly, I'm going to move more slowly. And those two are connected because I'm not slipping. Because if I were going to be rotating really fast but not moving very far, I'd have to be doing this. And you can see that the bits of the wheel, the bits of this disc, are slipping past the bits of the ground, which, you know, are my duct tape and calculator here. So if we move without slipping, if we're rolling like this and we're not slipping, how fast we rotate is dictated, or dictates rather, how quickly we translate. So those guys are linked, and you'll actually notice that I chose it so that the translational speed was omega times r. In other words, my translational speed is equal to my tangential speed, which is omega times r. And that works out. R is 2 meters, omega is 5 radians per second, and our translational speed is 10 meters per second. So all of that has to be so because of this, because it's rolling without slipping. But this is how you can do an energy problem if you've got rotation. You do just the same stuff you normally do for an energy problem. Look at work, it's equal to the change in energy. Figure out if you've got any work, and then figure out what kinds of energy you've got. Look at the final energy, subtract the initial energy. Look at the final energy, subtract the initial energy. Then you've got your equation, and you can just go and do lots of algebra and solve it out.